Hi guys, welcome to my YouTube channel. Today I want to talk about gases. There are three states of the matter: solid, gas, and liquid. Also, there is a fourth state called plasma, but it's rarely seen in our surrounding environment. Fire is one of those examples. Look at these three balloons here that I have blown into different levels. Let's talk about what's in this, like the blue one, the red one, and the yellow one. If you look, what happens if a balloon, uh, actually, when a balloon depletes or go flat, what happens is that when you have a balloon, which is a pressure that is higher than the environmental pressure a little bit, there is molecules of gases that are condensed in it, so that volume is small. As the balloon blows out, the molecules become more and more mm, sparse, or how to say, less condensed, and they actually fill out the entire environment until the balloon is completely uh, flat, and the entire environment is actually filled out with the gas that was actually inside the balloon. So as you see, the volume is going to increase as the pressure actually decreased to atmospheric pressure. Okay, that's what happened with these three stages. Let's just plot the volume versus the pressure. It's a logarithmic plot like this, with the pressure and the volume, and it's like this. So the pressure actually goes higher and higher as the volume of the gas becomes smaller and smaller. Okay, so this gas with the smallest volume, because the gases inside it has the highest pressure, so that's the blue one right here. The yellow one, this one, is the one that I could represent maybe with a marker of correct color. I don't have a yellow, but I have a light green, so I could say this is my yellow balloon. And then oh my bad, yellow should be the one that has its gas sample has the highest volume. If it depletes, it means those gases that were in there are now spread into the environment. So that's the yellow one. And in the middle, I have the middle sized one, which is the red balloon. So you could see how the pressure is actually raised as you go from blue to red to from yellow to red to blue, with the pressure being raised. Okay, and it's a logarithmic again relationship. There is an equation for gases, and that's called the ideal gas equation, and we're going to discuss that. And to be able to solve problems with gas problems, we need to be able to handle that one. So that's PV equals nRT. But interestingly, with pressure being the pressure of the sample in atmosphere, volume being the uh, volume, size of the balloon, or whatever, in liters, and moles is just, n is just moles, there's no dimension. R is a constant, and it's 0.0821, and temperature should always be in Kelvin. So be careful about these units. They should be in their proper state if you want to solve an equation for a gas. Okay, so let's talk about a specific examples if we want to solve a problem in a situation where we have a gas. Usually there are three in most chapters that represent gas problems. There are the Boyle's law, Charles law, and the Gay Liouville's law of gases. But these are all thought equations derived from this grand ideal gas equation, and I'm going to discuss all the three. And if you want, you can also memorize the name for the Boyle chart or Gay-Lussac, but there's really no need to know them if you can work with this equation. Okay, so in most of the gas problems you don't have to deal with all the three or all the four variables. Usually two of them are being discussed. For example, P or are being varied. P and V, like the problem we had here where the temperature remains constant, and P and V are going to actually change. Also, if we have a gas that we could see the molecules, when we let it go in a room, N would also be constant. So, my bad, N is not changing. So then it's P and V, and we tend to have those variables on one side of the equation and put all the constant on the other. So to set this equation, all variables on one side and all constant on the other side of the equation, we could then pick the variables and write them two times, and that would be the equation of either Charles' law, Boyle's law, or Gay-Lussac's law, and we just actually ignore the constant ones. So imagine the situation that I just told you, where in it N and T are constant, R is a constant by itself. Let me just put these constant values in another color that would help. I would put them in red so we know that we're going to ignore them. Okay, and as you see, I could now take P and V and say myself, okay, P1V1 equals the P2V2, because these are only changing things. So that's one. I'm just going to write it down here, a small P2V2, and P1V1 as well as P2V2 represents a state 1, a state 2, like when you have a balloon and then you blow it up, okay? Or where you have a gas sample, you shrink it or you raise the temperature or whatever. So that's the state 1 and the final state or state 2. Let's say now instead of the P and V being varied, we kept P constant and V and T are changing. Okay, so if V and T are changing, then that would be P, N and R that are constant, and we have PV equals nRT. So we need to move all the constant to this side and all the variables to the other side. That would be V, because it's all of these are multiplication. So when you move anything to the other side, it moves down if it's on the top. And because in this form, all these variables are on the top, when you move either of them to the other side, it shows in the denominator. So T comes down here, equals nR as well as P shows down on the bottom. So again, I could say ignore this and I do V1 T1 equals V2 T2. So that's a state 1. On one side I put a state 1 and on the second side I put a state 2, and this would be the relationship that is going to be useful. So one other relationship is Vt, so V over T 1 1 2 2. Okay, that's when volume and temperature are those that are changing. Now let's say we have another situation when so in this one we know that T is constant, in this one we know that P is constant. Let's assume, what if V becomes a constant? So if V is a constant, then you have P and T being changed. So P over T, if you move T to the other side, would be equal to NR over V. That is constant. So we're going to ignore this. In an equation or in a problem where V and T are, when P and T are being changed, you could say P1 T1 equals to P2 over T2. Okay, so these three are the most useful. You could also have a situation where three of those things like PV and T, both all three of them are being changed. So if you have that situation, volume is also changing. You could see that if I just move T, I could get PV over T equals PV over T, and a state 1, state 2. So you could see these three are the most used, but you could actually derive any other thing if you have n, for example, being changed. You could have many factors that many two equations and many three equations. You could get this and this being changed. Then you would have PV over n, and you would have 1 and 2 indices. Okay, but they're not as famous. The main point is to be able to rearrange this PV equals nRT. With this brief interview, let's walk into sample problems and see what are more important tipping points when trying to deal problems that are actually how to say important in gases. Okay, so that's what I want to do today here. And to do that, I'm interested to start with simple problems. As I go on, I would do more and more how to say harder problems, more challenging problems. Let's say the initial pressure of a balloon is 400 torr. Let's use my other marker so that I could write in a smaller, be more careful about my space. The V1, the volume, is 200 milliliters, and the P2 is being asked what would be the P2 if the volume is now decreased to 75 milliliters. Okay, so first I have to convert my pressure and volumes to liters. Volume to liters would be very easy. This much liter, just divide by 1,000. This much liter, because each 1,000 milliliter is a liter, and this guy 400 torr, we know that 760 torr is 1 atom, so we just get 400 divided by 760 to see what the pressure would be. And the pressure would actually happen to be, if we do this, we would have the pressure being 400 torr equals to 0.526 atmosphere. And then the problem is, which situation am I using? When the problem doesn't provide any information on temperature, it means the temperature is being constant, so the pressure and volume are the ones that are changing. So PV equals nRT, and I could just say P1V1 equals P2V2, P1 being 0.526 times 0.2, that's V1, equals to P2, I don't know, times, oh my bad, times 0075. So if I move this, it would go down. This means this times this divided by that, and P2 then becomes 1.4 atmosphere. And if you times this by 760 times 760 torr, it would then be 1066 torr. So that's that. Let's just move on to yet another example. Imagine if the problem told you that the pressure is pressure of our gas sample is 700 torr. It's going to be P1, while the volume of it is 2.5 liters. And then if we raise the pressure to 5 atmospheres, what would happen to the volume? How much would the volume shrink? Because if we exert pressure, the volume should decrease. So 700 torr, that's a little bit problematic. 700 divided by 760 to get at, and that would give us 0.921 atmosphere. Okay, so that's what we have for pressure. Again, the problem is PV equals nRT. T and N are constant, so again we're going to have P1 V1 equal P2 V2. P1 is just 921 times 2.5 equals 5 times the P2. The V2 we don't know, so 2.5 times this divided by 5, and that would give us a volume of oh my bad, the V1 I made it let's take it as 40 liters, so it's a 40 liters gallon or balloon or something that is inflatable, and it has this much pressure. So instead of this 2.5 here, I should put 40, and then for the V2 when it's shrinking I will get 7.37 liters. That's the final volume. Okay, so that's how you do it. That's the second sample. Yet second problem. Let's do yet another problem. So let's say the temperature of a sample is 27 degrees centigrade and the volume is a V, we don't know. It's a given volume, but let's say what would be the T2. So the T1 is this. If the volume is doubled, so if the volume is doubled, if we take it as V, it would be 2V at the final. Again, you could see it's T and V that's being changed, that's being constant. So it's going to be, if I just write down PV equals nRT, I could then take D to this side and put P to the other side. That would be nR over P is going to be my V, my volume over T. Okay, so I'm going to use volume over T to solve it, because volume and T are temperature are changed, but temperature must be in Kelvin, and that's 27 plus 273, that gives you 300 Kelvin. So you have to change the temperature to Kelvin before you could deal with the problem. So let's do this. The volume V1 is just V divided by 300 equals to the volume 2 is 2V divided by temperature that we don't know, T2. So because these V's are the same, we could just drop them off both sides, and then I could put the T to the other side and 300 to the other side. That would change, that would actually solve my problem, being T2 equals 2 divided by 300. Actually 300 should be on the top. 2 times 300, so 600 Kelvin. If I just take 600 minus the 273, it would be 327 degrees centigrade. That's the temperature. If you just double the if you just double the volume, okay, let's go on. Let's do this one. It says a volume of a sample is 2.5 liters and the pressure is 760 millimeter Hg. That's exactly 1 atom. What would be the volume if the pressure is 630 milliliter Hg? So 630 divided by 760, it would be my final pressure. That's 0.829. And I got to do P1 V1 because that's P and V that's changing again. Okay, so that's 2.5 times 1 equals 0.829 times V2. So the V would, as we mentioned, the V would actually increase because we're actually lowering the pressure. So that would be this divided by this, and it would give you 302 liters. That's the V2. So that's this problem. Let's also do yet another problem. And that would be if the volume of a sample is 3 liters and the temperature is minus 20 degrees centigrade, what would be the volume if we raise the temperature to 27 degrees centigrade? So minus 20, again, minus 20 plus 273 is 293 Kelvin, and 27 plus 273 is 300 Kelvin. Okay, so that's these temperatures. Temperature 1 is this, temperature 2 is this, volume 2 is that, and again it's V over T. Okay, because V over T would be equal to NRP, NR over P, PV equals NRT. If we just rearrange it, we will find that relationship. So V1 is 3, T1 is 293 equals V2, we don't know, and T2 is just 300. And from this we will get V2 to be 3.56 liters. Okay, so that's how this changes. Okay, this is how it changes. Volume would be this, and that is our final answer. Let's go to do a little bit more challenging problems, and I would wrap it up with this example, as I will do a second video and do more challenging problem on gases. So let's go on and try to do this example. When we want to compute the molar mass of butane, molar mass of butane gas, the 3,4H10, if 3.69 gram of it occupies a space that is 1.53 liters with a temperature of 20 degrees centigrade and the pressure of 1 atmosphere. So that is 20 plus 273, so that would be 2 93 Kelvin, and then so 293 Kelvin, and that's it. So for the molar mass, we only need to know N, and because we have the grams, we know that the molar mass is M divided by N. So to find out N, PV equals nRT. So if we take solve for N, N would be PV, moving R and T to the down here, we could find N. Then N is P, which is 1, times V, which is 1.53, divided by R, which is 0.821, times T, which is 293. And that would give you an N that is 0.0636. And here I go down to put 3.69 divided by 0.0636, and molar mass, I would find it to be 58 gram per mole. If you also add 4 carbons and 10 hydrogens, you would still get the same exact amount, but the problem actually may not give you formula for butane. I just provided to show you that we could check out, but the problem does not give you this, so you have to follow this route. That is for today. I want to wrap it up here. Next video I will do more and more example on gases.